Okay, so we have some word problems that go along with the infinite geometric series problems. So here we have a pendulum that's released to swing freely and travels 18 inches on the first swing. On each successive swing, so successive means each next swing after that, the pendulum travels 80% of the distance of the previous swing. What's the total distance the pendulum swings? Now, you're probably thinking, well, like a pendulum eventually comes to a rest, and yes, it does, but the moments before it comes to a rest, it's moving such a minuscule amount, that 0.000000001 tenth of an inch, that you're ultimately adding zero essentially anyway. So it's not saying that there's a finite number of swings, like it's only going to swing 10 times or it's only going to swing 20 times. It's going to swing infinitely until the distance is so negligible that you're practically adding zero, which means when it stops, you've already taken that into consideration. So just kind of think about how that works and how the movement becomes smaller and smaller and smaller. We kind of draw a visual of this. That first swing, it's going to go 18 inches. So start to end is 18 inches. And then on the second swing, it's going to come back, but it's only going to go 80%. So we can think of like 0.8 times 18. And then it's going to go back this way, 80% of this one. So it's going to be 80% of 18, which we can write as 0.8 squared times 18. So if we try to like write this out as like my first term and then my second term and then my third term, we wrote that out as our sequence, we would have 18. And then since it's a series, I'm going to put plus signs. The next term is 18 times 0.8. The next term is 18 times 0.8 squared. What would my next term be? 18 times 0.8 cubed, and then it's going to keep on going forever and ever and ever until that 0.8, to the 15th power is so small that it practically doesn't exist. So as we think about what our first term and our ratio is, we can kind of see that this 18 is the same thing as like 18 times 0.8 to the 0 power. Think about this as to the first power. So that 0.8 to the 0 power, this fits into my rule. This right here fits into my pattern, if you will, my sequence. So hopefully you can identify from that A1 is going to be 18 and R is going to be 0.8. So as we identify those pieces, now we can go ahead and plug that into our formula. So S equals my first term of 18 over 1 minus that ratio of 0.8. So multiplying that in our calculator, dividing that in our calculator, we should get 90 inches. So the pendulum swings for 90 inches before coming to a complete rest. All right, so now we have the rubber ball or the basketball type problem, which is a little bit different because you got to think that pendulum swinging, it's returning at 80% on each swing, but a ball is bouncing, it's going up and down, so it's kind of got two directions with it. So a rubber ball is dropped from a height of 60 feet. Each bounce takes it to 2/3 of its previous height. What's the total vertical distance the ball travels? So if we try to think about this, that initial drop is going to be 60 feet. Then it's going to bounce up 2/3 of that 60 feet. Well, what happens to that ball? Is it going to drop down only 2/3? Well, no, it's going to have to drop down that exact same amount because whatever goes up has to come back down. So we really have that 2/3 of 60 two times. And then it's going to go up again. And now this time it's going to go 2/3 of the 2/3 of 60 that it just went. And it's going to have to come back down. And since it has to come back down, well, now we have that distance twice. And it's going to continue doing that. So as we think about what this means, we can kind of write this term as 2 times 60 times 2/3. And then this next term is going to be 2 times 60 times 2/3 squared because we have 2/3 two times. So as we think about our sequence, well, my initial distance is 60 plus 2 times the 60 times 2/3 plus 2 times the 60 times 2/3 squared, plus my next one would be 2 times 60 times 2/3 cubed, and it would keep going on and on and on and on and on forever. So as we think about the difference between the last problem that we just did and this one, if you think about putting this as an exponent of 1, can you put a 60 here times 2/3 to the 0? But we still need this extra 2 out here. Is this equal to the 60? Well, no, it's not. So this is not part of my sequence. It doesn't follow the pattern. So go back for a second. Look at this sequence here, how this 18 times 0.8 to the 0 power, 18 times 0.8 to the first, 18 times 0.8 to the second, 18 times 0.8 to the third. It all followed that pattern. So this 18 is the same thing as 18 times 0.8 to the 0. Well, that doesn't happen here. If I have 2 times 60 times 2/3 to the 0 power, that's going to give me 120. That's not going to give me 60. So that doesn't fit into the mold. So what we need to realize is that this right here, that's kind of our sequence. That's our sequence. We have 60 plus 120 times 2/3 plus 120 times 2/3 squared plus 120 times 2/3 cubed, and so on. So this 60 is like just the extra. It's just the initial drop. So as we think about what our first term is, what we really need to think about is our first term is 120 times 2/3 right here. That's our first term in our sequence, and this is the sequence. That's where all the patterns start. So 120 times 2/3, that's my initial pattern, my initial term in my sequence. Here's the sequence that we're talking about, up, down, up, down. The fact that there's 2 motions all over 1 minus that ratio of 2/3. Well, that's going to give me all the vertical distance that it goes up and back down, up and back down, up and back down. But we also have to then add in the initial drop. That's what this is right here. So when we do that, when we type in 120 times 2/3 over 1 minus 2/3, you're going to get 240 feet. That's just the up and downs that it's going, plus the initial 60-foot drop is going to be 300 feet. All right, try your homework.